All right, today we're going to talk about Unit 1, Lesson 2, horizontal, vertical intercepts, and symmetry. Notice I'm speaking about horizontal and vertical intercepts. I could be talking about, actually, I will be talking about horizontal intercepts are also x-intercepts. Vertical intercepts are also y-intercepts. That's the first thing you need to know. And a horizontal intercept is defined to be any point on the graph of an equation that has a vertical component of 0, i.e. the y-coordinate or the vertical component is 0. So any point that has this form right here, a comma 0, that's defined to be a horizontal intercept. In like manner, a vertical intercept is defined to be any point on the graph of an equation that has a horizontal component of 0. That is any point that has the form 0, comma b. And we certainly have had lots of experience with vertical and horizontal intercepts, x-intercepts, y-intercepts. Okay, so let's, considering only equations in x and y, we find the x-intercept by setting the y variable equal to 0. And we find the y-intercept by setting the x to 0. So x-intercept, y is 0, y-intercept, x is 0. So here we go. Example 1, find the x and y-intercepts of this quadratic, y equals x squared minus 4x minus 5, analytically, and then we're going to show the graphical solution. So what I would like for you to do when you find an x and y-intercept, state what you're going to do. And so I'm going to find the x-intercept first, and I'm going to write this down. X-intercept, I let y equal 0. X-intercept, let y equal 0. So I'm going to put 0 in for y right here. Notice I'm 0, and then I'm going to solve this equation. That's an easy equation to solve. That's a simple quadratic. We reviewed factoring quadratics in our review section. This guy factors pretty quick. We notice I have two numbers that multiply together to -5 to add up to -4. Those two numbers are going to be x minus 5 and x plus 1. -5 times +1 is -5. -5 plus 1 is -4. Now I'm going to use the zero product property, and this is going to tell me that 0 is equal to x minus 5, or 0 is equal to x plus 1. That tells me that 5 is equal to x, and -1 is equal to x. So my x-intercepts, it looks like I have two x-intercepts. One is going to be 5, comma 0, and the other is going to be -1, comma 0. And what we're going to do is come over here on the graph, and we're going to graph those x-intercepts right away. I'm going to do my graph in purple. So I'm going to have -1, comma 0 right there, and I'm going to have 5, comma 0 right there. And if I remember about the graphing, see if I can't zoom out. I think I'm out all the way. I am. And if I remember about quadratics, that's going to open up and it's going to have a minimum point, and that minimum point is going to be exactly between the two x-intercepts because of the symmetry of the parabola, which is the graph of the quadratic, but we don't have to worry about that right now. So the next thing we're going to do is find the y-intercept. We're going to find the y-intercept, and we're going to write that down here. The y-intercept, we're going to let x equal 0. And if I let x equal 0 in this, easy, y is going to equal 0 squared minus 4 times 0 minus 5. And we see that y is equal to -5. So my y-intercept is going to be 0, -5. And I'm going to plot that bad boy over here. Again, I'm going to plot it in purple and blue, or whatever you want to call that color, 0, -5. And so I know from Algebra 2 that this vertex, as I spoke to before, is going to be halfway between here. So about halfway between here is going to be about right there. And I'm just going to graph this bad boy. Oh boy, oh, that must be my pen. That's a crazy graph. Okay, back taping. So, okay, the next thing we're going to do, this is my graphical representation. Over here, I have the two x-intercepts and I have the y-intercepts graphed onto that particular graph. Now, on example number 2, I'm going to name the x and y-intercepts of the given graph. This is certainly not the graph of a function, and later on we'll talk about more graphs that are not functions. This is not a function, just as a side note, not a function, but it still has x and y intercepts. So this is not a function, just as a little side note. So let's name the x-intercepts. The x-intercepts, notice I'm abbreviating intercepts, int, period. The x-intercepts, let's see, the x-intercepts are the points that have a y component of 0. So I have, here's one rascal, here's another rascal, and here's the third x-intercept. So my x-intercepts are easily -3, 0. 3 halves, 0. And 4.5, 0. And why they chose to write this is 4.5 and that one is 3f, I didn't know. Both I did. Now I want the y-intercepts. The y-intercepts are the points that have an x component of 0. And notice I have 3 of them. Bam, bam, bam. And we'll list them from least to greatest. Here's the least. It's going to be 0, -3.5, y-intercept. And 0, -4/3. And 0, 3 are the y-intercepts. This is the graph. This is something that we have not, it doesn't matter. Well, this is actually also the graph of a quadratic function of x, because I could solve that for y, so it is a function of x, just as a side note, but we're not going to solve it for y to find the x and y intercepts. We're going to use the process as we discussed. So what would you like to find first, Billy, the x or y intercepts? Okay, Billy, let's find the x-intercepts first. How do I find the x-intercepts? I let y equal 0. True or false? That's true, Billy. So I'm going to let y equal 0. I'm going to put y in there. I'm going to go 9x squared. Do I need to write the 4y? Not really, because I know that 4 times y is 0, and so I'm not going to put the 0 there. And I think we're okay with that. Now I'm going to divide by 9, and I have x squared is equal to 36 divided by 9 is 4. What squared is 4? X is equal to 2. Correct? Or -2. So here's my x-intercepts. 2, 0. And -2, 0. So those are going to be symmetric. So we're going to plot those bad boys right there. This guy here is going to be 2, 0. And this rascal here is going to be -2, 0. Next up will be, we will find the y-intercept. And we find a y-intercept, you'll know, by let x equal 0. So we find a y-intercept, we let x equal 0. No, 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 yes. So if I let x equal 0, this I simply have the equation for y is equal to 36, and y is equal to 9. Therefore, y is equal to 9. And my y-intercept is going to be 0, 9. So let's plot that bad boy right there, 0, 9. And we will graph. Oh, heavens. It looks like this parabola opens down. Why would that be? Well, let me tell you why it would be. If I did solve this equation here for y, look what I would have. Do you have enough room on the bottom? You'd have enough room on the bottom. If I did solve that, what would we have? We would have 4y is equal to negative 9x squared plus 36, and then I would divide by 4, but then the coefficient of the leading term there would be negative. The a would be negative, therefore the parabola would be concave down. Okie dokie. May I go on to the next page? So symmetry is something that we talked about, I know, in geometry. We did talk about geometry, symmetry. It's one of those things that we mostly talk about flatland symmetry. And I think we talked about rotational symmetry. It's not a big standard or a super important standard, but we did hit it a little bit. Here we're going to do analytical symmetry, and it will have some geometric connection, but this is more analytical symmetry. So here's what it means. A graph is said to be symmetric with respect to the x-axis if for every point A, B on the graph, A negative B is also on the graph. These definitions will be much clearer once we come up with a graph, a graphical representation. But you do need to know these definitions, and once you get them down, they're going to be very easy to know. You'll see how easy they are. Okay, a graph is said to be symmetric with respect to the y-axis, reflection over the y, symmetric with respect to the x is a flipping over the y, is a reflection over the x, and symmetric with respect to the y is a reflection over the y-axis. That's why if for every point A, B on the graph, negative A, B is still on the graph. If you notice, the y coordinates stay the same, and the x coordinates, you have opposite x coordinates. Here, the x coordinates stay the same, and you have opposite y coordinates. This is what's really hard. This easy visual. This is an easy visual. Easy visual, as you'll see in a little bit. This is an easy visual. This, however, a graph is said to be symmetric with respect to the origin if for every point A, B on the graph, negative A, negative B is also on the graph. This is not easy visual. It's not easy for everyone to visualize this. So this is not easy visual. And we will give a visual example of all of these in a bit. So here's my example. For each of the given points, find a point that is symmetric to that point with respect to each of the three types of symmetry. So if I have the point 5, negative 6, and I want a point that is symmetric with respect to the x-axis, I see up here, the x's remain the same. The x's remain the same, but the y's go opposite. So that's that point symmetric with respect to the x. symmetric with respect to the y, what happens? The x's go opposite, the y's remain the same. So the x's go opposite, so I'm going to go -5, and the x's remain the y's remain the same. X is opposite, y is the same. With respect to the origin, look what happens. I take the opposite of both coordinates. So with respect to the origin, this point becomes -5, maps to -5, comma 6. Pretty, on a scale of 1 to 10, 10 being very difficult to do, this is like a 2-ish. Take a moment and fill in the blanks for B. Okay, let's quickly find the point with respect to x, symmetric with respect to x of this. And we notice that the x's remain the same and the y's change. With respect to the y, the x's go opposite and the y's remain the same. With respect to the origin, both coordinates take on the opposite of what they started with. Okay, super easy. We will use the above definitions to sketch the desired type of symmetry. This example, we're going to use the above definitions to sketch the desired type of symmetry. So number one, we're going to sketch the image of the given graph symmetric with respect to the x. And we notice these 3 points are on the graph. So I have 1, 1 on the graph. I plot them in there. I have 1/2, 2. That's 1/2, 2. And I have 2 1/2. And I want this symmetric with respect to the x-axis. So I'm going to flip it about the x-axis. Before I do that, because it's sometimes hard to see the visual, the graphical representation, I'm going to go ahead and write the points down. So 1's going to be, if I'm going to go x, the x's remain the same, the y's go negative. No, 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 yes. The x's remain the same, the y's go negative. The x remains the same, the y goes negative. So now I'm going to plot those 3 points. 1, -1. I do this symmetry in blue. There's 1, -1. 1/2, -2. Was about right there. And 2, -1/2 is going to be right here. And you can kind of see the symmetry taking effect. So here we go. Oh, that's very nice. As stated, you can see the reflection of about the x-axis. The red graph, if it's reflected about the x, becomes the blue graph. So let's do example number 2. I want to sketch the image of the given graph with respect to the y-axis. The points 3, 0, 7, 2, and 7, -2 are on this graph. Let's go ahead and plot those points just for giggles. This is 3, 0. This is 7. Let's see here. 1, 2, 3, 4, 5, 6, 7. This is 7, 2. And this is 7, -2. And what I do, I want to reflect that about the y-axis. So if I'm going to reflect it about the y-axis, I come up here to my example here. And I notice if I'm going about the y's, the x's go opposite and the y's remain the same. X's go opposite, y's remain the same. So I'm going to name the new points -3, 0. -7, 2, and -7, -2. Okay? X's remain the same. The x's go opposite, sorry. and the y's remain the same. Double check. Let's see here. The x's go opposite, the y's remain the same. The x's are opposite, and the y's remain the same. Let's plot those points. We'll plot them in blue. I have negative 3, 0. I have negative 7, 2, 3, 4, 5, 6, 7, 2. And I have negative 7, negative 7, negative 2. And so we can see I'm going to sketch the reflection about the y. Like it be a little bit more curved, but that's nice. And that's a reflection about the y-axis. And you can see the blue graph is a reflection of the dark graph about the y-axis. All right? Let's see what we have here. I